Welcome once again to online classes. Today we are going to look at H.C.P unit cell, and we are going to look at the packing fraction of H.C.P unit cell. Packing fraction tells us how much space is occupied by the atoms in that specific unit cell and how much space is void or is remaining free or unoccupied by the atoms in that unit cell. With H.C.P, it can be projected in 2 dimensions and also in 3 dimensions. In 2 dimensions, we focuses with the area of H.C.P, while in 3 dimensions, we focuses with the volume. So, for today's class, we are going to look both in 2D and 3D because the two are related in somehow. So, let's start with the 2D. In 2D, we have said that we will focuses on the area of the atom, area of atom divided by the total area. So let's look at arrangement of the atoms. For example, we have atoms which are arranged linearly, or they are arranged. Okay, so we have also other atoms which are arranged. So these are atoms, and we still have atoms being arranged in this way. Okay, and in hexagonal we have 6 atoms, so let's call this as our atoms. So let's choose these two. We have 6 atoms which are surrounding one atom in the center. So you can see these atoms, we can name them A, or let's say A, B, C, D, E, F. So it means that now the area of H.C.P, which is A, B, C, D, E, F, because the area of the 6 atoms. If we connect these center atoms with any of the 2 atoms, it's going to form a triangle. So assume that this is the center atom which is surrounded by the 6 atoms. If we take any neighbor 2 atoms to it and we link them together, we can form a triangle. So it means we can have a triangle AB. We can have this triangle, we can have these triangles to every corner of the atoms. How many do we have? We have 1, 2, 3, 4, 5, 6. So we have a total of 6 triangles in a unit cell of H.C.P 2D. This, if we make this center atom, let's call it O, and we want to find this area of one triangle. Let's say this is our A and this is our B. So if you look at the distance between point A to the edge of this atom, we have R, and the distance between the edge of this atom B to the center of this atom is also R, the same R and the same R. So we can say then AB is equal to 2R, and also AO is equal to 2R. It doesn't matter capital R or small r. So now what is the area of a triangle? The area of a triangle is given by half base times height. Now we can introduce our height here from O to the middle of this point, and this is gonna give us our h that you are looking for. Remember AO, this distance to here is 2R, so this is 2R, and this triangle, the 3 sides are equal, and therefore let's say our triangle OAB is equal to 60 degrees. because these three angles are equal. This is an isosceles triangle, so both angles are equal, so each angle here is 60 degrees. So now if we were to draw it, let's draw triangle AOB. So we have our triangle here, so we have point O, we have A and B, and we see we're looking for this height here, which is H, and AO is 2R, okay, and this angle is 60 degrees. I want to look for H. I have 2R. We can apply our SOHCAHTOA rule, SOHCAHTOA, and here I have the hypotenuse, I have the theta, and I'm looking for this opposite, because H is opposite to theta, which is 60 degrees, and 60 degrees or 2R is up, in the hypotenuse to 60 degrees. So I can apply the sine rule to find this H here, and sin theta, we know sin theta is equal to opposite over hypotenuse, and our opposite, this is gonna give us sin 60. Our theta is 60, so sin 60 degrees is equal to opposite, which is H over 2R. So we can find H by saying sin 60 is root 3 over 2. So root 3 over 2 is equal to H over 2R, and that's gonna make our H is equal to 2R times root 3 over 2. 2 can cancel 2, making our H is equal to root 3R. So this is the value of H. So we can substitute, and then we find the area of one triangle. So our area is going to be 1 over 2R times base, and our base is 2R times 2R times root 3R. So 2 can cancel 2, making our area is equal to R times root 3R is going to give us root 3R squared. This is the area of one triangle, and there are 6 triangles, so the total area is going to be, so area total is going to be 6 times root 3R squared, and that's going to give us 6 root 3R squared. So this is the total area in 2D of the HCP. Now let's proceed and get, because we did say that 2D, when we are referring to packing fraction in 2D, we said is the area of the atom divided by the total area. Now atom looks like a sphere, and the area of a sphere is given by, pi r squared. Now we know that packing fraction in any unit cell is given by Z, and Z is the effective number of the atoms. Now in this case of 2D, we are going to have Z times the area of the atom, which we have found to be pi r squared, over the total area of the atom, which we have calculated to be 6 root 3R squared. Now what is Z? Z is the effective number of atoms in a unit cell, and from here we can determine the value of Z in 2D. So let's redraw our unit cell. So we have 1, 2, 3, 4, 5, 6, and we have one atom at the center, which is surrounded by all this. And then assume we have another unit cell that side. We also have another unit cell on the other side. So if we put our focus in these corner atoms, we find that it is surrounded by 3 unit cells. So we have 1 unit cell, 2, and this our original unit cell. So it means that every corner atoms in 2D HCP, every one corner atom is being shared by 3 unit cell. So it means the contribution of that corner atoms will be 1 over 3 times the total number of the corner atoms in that unit cell. So how many total number of atoms in this unit cell? There are 6, and that's going to be 1 over 3 times 6, and that's going to give us 2. However, if you look at this unit cell, 6 corner atoms are surrounding 1 atom at the center, and we are going to look at the contribution of the middle atom or center atoms, and it is only 1, so we are going to say is 1. So it means that our Z now in 2D will be the contribution of corner atoms, which is 2, plus the contribution of the center atom or 1, that middle atom, which is 1, making our Z to be 3 atoms. So we can proceed then and say then our packing fraction in 2D will be Z, and Z is 3 times pi r squared divided by 6 root 3 r squared. R squared can cancel R squared. 3 goes here into 3 ones into 2. Sorry, into 6 it goes 2, leaving our PF or packing fraction in 2D to be how many? Pi over 2 root 3, and this one give you 0,906, which is approximately 0,91, and in terms of percentage this one will give you 91%. So this is the PF. So it tells you that 91% of the total area in a unit cell, if you look at the unit cell in 2D, 91% of that unit cell is occupied by the atoms, leaving 9%, only 9% of that area is unoccupied by the atoms, or what we call void space. So this is how we calculate the packing fraction of HCP 2D. Remember, 2D deals with the area of the atoms, okay? So if you are told to prove that packing fraction is 0,901 or is 91% in 2D HCP, so this is how you can prove it. In our next slide, we are going to look at the HCP in 3D, which deals with the volume. And 3D we did say, so let's look at our 3D, and in 3D we did say it is volume. So in 3D we are looking at the volume of atom divided by the total volume in a unit cell, total volume. Now let's draw our HCP in 3D. So this is a little bit tricky. So let's draw our HCP. Okay, it's not that well drawn, but we'll try. Okay, so this is the front face, and this is the back face there, and then this is the face this side. And with the HCP in 3D, we have 3 atoms connected at the center, and we have each atoms on the face, and this one is connected toward the center of these 3, and then we have 12 atoms, corner atoms in 3D. So these are the atoms that we have. So how many atoms do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So upper surface there are 6 atoms, and down space, lower space or space, there are also 6 atoms, so 12 atoms in total. And also there are these 3 atoms at the middle, and also in each face of 1 unit cell there is 1 atom, so there are a total of 2 atoms. However, the distance between this one is h, and if you look the distance between these atoms to these atoms, if we are to show you the real arrangement of the atoms, then you realize that this distance here is a half of this, so we can put it as h over 2. Okay, so we can name it, let me write it properly, h over 2. So this height is the half of this height here. So this is how HCP in 3 dimensions looks like. Okay, so now let's start our calculation, because now packing fraction will just proceed. Packing fraction is equal to the volume of the atom over the total volume, and the volume of HCP is given by the area of that HCP times the height. Area of the HCP, we have calculated it from 2D, and the area we have calculated and we found to be 6 root 3 r squared. Okay, so let's look at this height h here. This h here is this h, the one we have in the center, which is a half of this big h. So I want us to redraw the one in the middle. So it looks like this. We have 1 atom in that center, and also we have these 3 atoms here, and these 3 atoms are connected to this atom, and then we have this h here. So this is our h over 2, this one here, and this one is connected to this. So this is what we have from the center. As I said, in reality, these atoms are arranged such that if we were to name them, let's say A, B, C, D, and let's say this point O. So the AB is close such that they are close to each other. A, O, B, A, C, D, this D, and are also in the same phase. So the distance between the distance between AB is 2r. Now we can connect this point here, and let's say we call it point X. We don't know this point X, and we're looking for this point, this height here, so that we can calculate the volume, because our volume is area times height. So now if we look at this point, let me now redraw it. This is hypotenuse, and this is H2, and this point, because it forms a right angle triangle, so it forms something like this, 2r, and then we have our h over 2, and this is our x. Remember, this is A, this is B, and this is O. I want you to remember that this O is the middle point between A and C and A and D. It is not any of these atom D and C. No. So now how can we find H? X. We can apply Pythagoras theories, which can say AB squared is equal to AO squared plus OB squared plus OB squared. Now what is AB squared? AB squared is 2r, so we're gonna have 2r squared, okay, is equal to AO squared. AO squared is x squared, is x, So it is x squared plus OB squared. OB squared is h over 2 squared. Okay, h over 2 squared. So now we don't have x and we're looking for h. So we need to come up with a way in which we can calculate the value of x. So how do we look at the value of x? Let's come here and redraw this x in another way. So I want us now to consider triangle ACD, this one here. I want us now to put our focus on this one here. We can redraw it and say this is our A, this is our D. Okay, let me draw it properly. So we have this now, this triangle. So if you look carefully, they are connected together. This is our A. Now this is our C and this is our D. However, there's a point between A. This point X is from the center of A to the middle point of D and C. So D and C at the middle point here, we have this length X. So this is our length X. Okay. Now that is our length X. So from this length, so this is our length X. Okay. Now this point between this point here to the middle point of this is R. So we have our R value here. So we have our R and we're looking for this X. Okay, we are looking for this X. Remember, this angle is 60 degrees. This angle is 60 degrees and this angle is also 60 degrees. But if we are to redraw this, we can then redraw it this way. Okay, so this is our X. This is the point D. So we can call it O for D. And then this is our A. And this is the middle point here. So this is our R. So now, this point here, this angle here is 30 degrees. And the other side is also 30 degrees, which is 60. So here is our 30 degrees. So I want this value of X, length AO, in this case, which is the length we are going to look for from this point here to help us determine the value of X. So if you look properly, I have R, I have theta, and I have X. So we can rewrite our SOHCAHTOA, and I have, if you look properly this triangle, then you see that this length A to this point here, this length here, if you compare to the theta, this R is adjacent to the theta, which is 30 degrees, and X is hypotenuse to this theta. And what am I looking for? I'm looking for X. So I have adjacent, I have the theta, I'm looking for hypotenuse, so I can use cosine. So we can proceed and say then cos theta is equal to adjacent over hypotenuse. And theta is 30, so we're gonna say cos 30 degrees is equal to adjacent, and our adjacent is R, is equal to R over hypotenuse, which is X, and cos theta, which is 30, cos 30 is equal to root 3 over 2 is equal to R over X. I'm looking for X, so meaning that our X is going to be R divided by root 3 over 2, and this is going to give the value of X to be 2R over root 3. So now we have managed to determine the value of X, and then we can proceed and substitute it from this equation, and then we can proceed and say that now 2R squared is equal to X squared plus h over 2 squared. 2R squared will be equal to be 4R squared is equal to X squared is 2R over root 3 squared plus h squared will be h squared and 2 squared will be 4. And now this gonna give us 4r squared is equal to 2r squared will be 4r squared, and root 3 squared will give us 3 plus h squared over 4. And what now from here it can be much easier now to calculate the value of h, and we calculate the value of h in terms of r by saying h squared over 4 is equal to 4r squared minus 4r squared over 3. And if we look on the right hand side, we can place this over 1, and the LCM here is 3. 1 goes into 3 3 times. 3 times 4r squared will be 12r squared minus 3 goes into 3 ones. 1 times minus 4r squared will be minus 4r squared. And then we can proceed here. h squared over 4 is equal to, now 12r squared minus 4r squared will give us 8r squared over 3, and we are looking for the value of h, and that will give us 3h squared. 3h squared is equal to 4 times 8r squared will give us 32r squared, and we can divide both sides by 3. Divide both sides by 3, and the value of h squared will equivalent to be 32 over 3r squared. And to get the value of h, we can then say h, we do the square root of everything, and that will give us 4 root 6 over root 9r, because when you put square root, 1r is going to go. Now, if you look at root 6 and root 9, they are similar, and that they are similar in there's a common factor, that is root 3, and we can proceed and say h is equal to 4. So root 6 divided by root 3 will give you root 2, and root 9 divided by 3 will give you root 3 and r. So this is the value of h that we have. So we have managed to determine the value of h. And what is the area? We did say that the total area of H.C.P is equal to, the total volume of H.C.P is equal to area times height, and we have managed to calculate the height, and therefore we can proceed now. Let me just go to the other side. Now we have calculated our volume to be equivalent to area times height, and our area we have calculated will be 6 root 3 r squared, and height now we have just calculated it to be, we found it to be 4 root 2 over root 3 r. So we can calculate the volume by saying that now volume is equal to area times height, and our area is 6 root 3r squared times height, which is 4 root 2 over root 3r. So root 3 can cancel root 3, and 6 times 4 is going to give us, so volume will be equivalent to, so let me just write here, volume is equivalent to 6 times 4 is 24. So we have root 2 r times r cube will give us, r squared times r will give us r cube. So this is the total volume of H.C.P in a unit cell. Okay, so now if you remember our diagram, which was looking something like this. Okay, so we add this one here, and we have 6 atoms, 1 2 3 4 5, the other one 6 at the back, 6, 7, 8, 9, 10, 11, 12. If we have this and we have one atom on each face, and we have 3 atoms here, 1, 2, 3, which were connected. Okay, yes, so this is what we have from the previous slide. So now let's look. We want to calculate the volume or the packing fraction, and we say that packing fraction in 3D is equal to the effective number of the atoms, which is Z, times the volume of the atom, divided by the total volume, right? So now we have calculated the total volume, which is 24. This one is our total volume. Okay, so we need to calculate the volume of the atom and the effective number Z. So if you look at the atom, looks like a sphere, and the volume of a sphere is given by 4 over 3 pi r cube. So that's the volume of the sphere. So we have the volume of the atom. Let's calculate Z. Now, if you look at Z, which is the effective number of the atoms, or the contributions of the effective number of the atoms. So now let's look at each corner cell. Remember, we did say in the previous, when we're looking at 2D, so this is 1, 2, 3, 4, 5, 6, and with one atom at the center, okay, for every unit cell. Now, I want you now to be careful here. Let's take the upper part of this H.C.P. Now, let's take at the upper part. If we put our focus on this atom, these corner atoms, so just like we saw, there's one neighboring unit cell. Okay, so how many unit cells are there? 1, 2, and this one 3. So meaning that in one phase, this one alone, if we look at this one, and let's assume that we also have another atom on the top. So you can see, if we have another layer of H.C.P on the top, you're gonna find that these corner atoms, only one corner atom is going to be shared by 6 atoms, because in this one layer there are 6. So there are 3, 1, 2, 3. There are 3 unit cells, and another layer on the top is also going to be 3 unit cells. So it means that one corner atom, just one atom like this, is being shared by 6 atoms. 6 atoms. So it means that 1 over 6, which is 6. So it's going to be 1 over 6, because 6 is the total number of atoms which are sharing this one atom. And how many atoms are there in H.C.P? There are 6 corner atoms. 1, 2, 3, 4, 5, 6 on the top, and also 6 below. So there are total of 12 atoms in the entire one. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12. And this gonna make us have 6 times 1, 6 into 2, 12, it goes 2. So we're gonna have 2 atoms. Okay, now those are the contributions of the corner atoms. They contribute to 2. Now let's look at these atoms in the red. So you have 1, 2. Okay, how many are they? Because now if we are to put another layer of this atom beneath it, we are going to have this one center atom is being shared by another layer of H.C.P that is below this one. So I'll assume that it is this one in red. So if this is 1, let's say this our original is 1, then the one below it is 2, and the one in blue is 3. So if we take into consideration this red one below is being shared by layer 1 and layer 2. So it means that one center atom is being shared by 2, okay, by 2 layers. And how many center atoms are there? There's this one which is being shared by layer 1 and layer 2, and there's this one on top of layer 1 which is being shared by layer 1 and layer 3. So meaning that there are two, because you have 1 and we have 2. So it is being shared by, there are 2 of them, and each one is being shared by 2 layers. So that's going to give us 1, and that's going to give us 1 atom. Okay, now let's look how many atoms are in the center. There are 3, and this 3 is not shared by any. They are 100% in each layer. This one, 1, 2, 3. So we have 3 atoms at the center or in the middle. Now, how many Z? Z now contributes to how many? It contributes to 2 atoms plus 1 atom plus 2 atoms. Sorry, plus these 3 atoms, and that gives us 6 atoms. So our Z value is 6. So from there we can calculate our packing fraction in 3D, which is going to be Z, and our Z is 6 times the volume of atom, which is 4 over 3 pi r cube, divided by the total area of the total volume of the atom, which is 24 root 2 r cube. So if we proceed, let's put this, let's write this, that our packing fraction is given by Z, which is 6 times 4 over 3, which is the volume of the atom, pi r cube, divided by 24 root 2 r cube. So this is the same as saying r cube will cancel r cube. 3 goes into 3, 1 into 6, it goes 2 times. So 2 times 4 is 8. So we're going to remain with 8 pi over 24 root 2, and 8 can goes into 8 once, 8 goes into 3, into 24, it goes 3 times, and that leaves our packing fraction in 3D to be equal to equal to be pi over 3 root 2. So this is the packing fraction. That's the packing fraction of our 3D, which is pi divided by 3 root 2, and this one will give you approximately 0.740, which if you write it in terms of percentage, by multiplying by 100%, by 100, we are going to get 74%. So this is the packing fraction or atomic packing fraction in 3D for H.C.P. So it tells us that for 3D H.C.P, the 74% of the entire volume of a unit cell is occupied by the atoms. This leaves 26% of the entire volume in H.C.P in 3D which is left void or vacant. Okay, so this 74% is what we'll say occupied space, occupied volume, and 26, making 26% to be free. Okay, to be free. So you can be told to prove that the packing fraction of H.C.P is 74%. So this is how we prove it. Okay, thank you so much for watching. Like, share the video, and subscribe if you have not subscribed. Thank you so much. Welcome. See you next. Bye.